Okay, so right. So in class we essentially stopped after stating the lemma, the Schmidt decomposition, which was the following: that you have a bipartite state, then you can express it in this form, right? Where UI and BI are orthonormal bases, and CI are non-negative. Okay, and how do you prove this? Well, so let's start. So this is the proof sketch. It's almost a full proof actually, but okay. So the idea is that you write psi. Uh, so the most general psi, right, one can express that as follows. So you have some coefficient, and you have some ij over here, and there's a sum over ij. Now we can treat alpha as a matrix. So alpha ij you can think of as indexing as the elements of a matrix, and then so one can suppose it's A. So one can write an SVD, singular value decomposition, as follows. So where U and V are unitary and sigma has the, so this is diagonal and positive, and basically contains the singular values, right? Okay. So now what one can do is one can easily check that this is true, which is that one can write IL sigma LM B M right? So this is just expressing the mix here, and the sum is over L and M. Okay, I and J. And now it's quite straightforward because one can extract. Yeah, maybe I should not have written sigma as the letter. Maybe let's just write it as D. It might be a bit confusing. Okay. So so now what one can do is one can write BLM sum over LM, and then one can write sum over I, UIL acting on a sum over J, BMJ acting on J. And then this thing one can call U sub L. Okay, and this thing one can call V sub M, right? So, and these are again orthonormal because you're multiplying with orthonormal entries. So you get a new basis, and now one is left with the LM UL VM. And DLM is diagonal, so one of the summation indices basically just becomes Kronecker delta. So you have DL. So let's call the singular value CI. So this becomes CL UL VL. Yeah. Okay. So that completes the proof of the Schmidt decomposition, right? This is the form that we asserted it would have. Diagonal, and we can just say CL. CL as entries. Okay. Good. And then, so there's an exercise in the notes that asks you to extend. The exercise is extend definition of entanglement to two parties. That's part one. And part two is does 0, 0, 0 plus 1, 1, 1, 2 satisfy your definition. Okay. So those were the two questions that you wanted to look at. Now let's look at the next section, which is about POVMs. So the definition is as follows. So suppose, so let S be a register Okay, and this earliest be the Hilbert space associated with that. Okay, and so then POVM. So a positive operator valued measure is a set of um, positive semi-definite matrices. M1 to say MK. And so basically each is belongs to positive on uh, S, right? Like that. X. Okay. Such that the sum over mi, I going from 1 to k, is identical. Okay. And the elements of mi are called the POVM elements. That's the definition. And mi are called elements of the POVM. So POVM. Okay, good. So here's the axiom. So this is in line with what you were saying, that you wanted to ask what is the most general measurement one can have. Okay, sorry, that was okay. So what was the most general axiom one can have? And the most general axiom one can have is the following. So given a POVM M above, um, a quantum state rho in S, the probability that outcome I is obtained under just S is measured is this MI. Okay. Um, and the nice thing here is that so one can show that this is the most general form of a measurement one can have in quantum mechanics using linearity arguments and uh, conservation of probability. So interesting is that so one can show that POVM are the most general um, type of measurement in quantum mechanics. Okay. And this includes cases where an extra system is used to measure extra system. Is used to make a joint measurement. Okay, good. And the other thing is that axiom, the one that we stated, it's numbered 54, because axiom 54 doesn't really say how. Say 54. doesn't say uh, anything about the post-measurement state. Okay. And so what that means is that okay, and why is that? Because it's actually not unique. Okay, and post-measurement state can be obtained if the measurements are specified as follows. So you're given the Krauss operator, or also called the measurement operators corresponding to the POVMs. Okay. So here, instead of considering just the positive matrices M, one can consider MI, which are defined as MI dagger MI. So these are by definition positive. Well, one can also check that they are positive. And so n are just arbitrary matrices. Okay, so if n are arbitrary matrices, then M is positive. So given these m's, given these n's, the probability that you have outcome I would be given exactly as in XM54. And the post-measured state, so the post-measured state, measurement state, sorry. So the post-measurement state, an outcome I is Ni rho Ni, but normalized. Right? So you have to normalize its phrase Ni rho Ni. Okay. So this is all I wanted to say about POVMs. Now, the next thing I wanted to ask was, the next thing I wanted to tell you was what is the most general operation, right? So here we just looked at the most general measurement, and then we saw that one could look at post-measurement state in a certain way. But what one can also ask is, what is the most general um, transformation one can do on a state? And these are called quantum channels. Okay. So I think I'll stop here for a minute. And,